That's all.
All right. I actually didn't say either way. What, is this my screensaver? Yes, it is.
We'll have to warn Gary's being recorded, too.
I don't know why the server's got two digits.
It's not that much data, really. If you just do this, it's not that bad.
Hi, this is Matt Sykes.
Hey, this is Gary Singh.
Is it any cooler than it was yesterday?
This is me here, and I don't think Gary's very smart.
This is getting recorded. Yes.
I can't imitate him here. Oh, Peter, thanks for joining. I know it's late on your time zone.
Yes.
Peter here?
No, that was Peter Hancock from the UK. Let me grab Peter.
You're not on mute. Would you like to be on mute?
All right, I think we've got enough to get started. Matt, this is the playback for operational metrics.
I have one. I have a pop.
And those folks on the phone were recording this, so.
Okay.
All right.
So in 1.4, we were asked to do some work for operational stuff, and I guess this focus today is going to be on the metrics piece. So this is going to go from pretty low level to high level. If you have questions, you need to ask them, preferably as they come up. Don't hold the question. That's just kind of how I like to run with it. So let's start with an overview. The basic gist is Fabric has a number of things that we wish to be able to monitor in terms of making sure that things are healthy, that things are not going out, running away from itself. Things like we've had cases where applications are written that open up connections to a peer, forget to close them. We leak connections, we leak gRPC sessions, we leak resources. Things get slow, things start becoming problematic, and we can't figure out what's going on. So we'd like to be able to detect when that sort of thing happens, run away, any resources that are running away. That's the first one. Other things, we'd like to have an idea of how much time we're spending in various phases of blockchain processing. So as we do transaction processing, we want to know how much we're spending in validation, how much we're spending in commit, how much we're doing in storage, how many requests we get, what chain codes are being invoked, how often they're being invoked. These are the kinds of things that you get from doing metrics. So that's the basic gist. The goal in 1.4 that I've had is to basically get us on the board. And what that means is find a handful of metrics from each of the components and surface them. I want to say clearly right now that I know we will not have all the metrics people want. I want to say clearly I know that we're not going to have meaningful metrics necessarily in every domain, but we have something, which means we have a starting point. And as soon as you have a starting point, it's almost always easier to add to the base that it exists. So think of this as something that's going to change over time. This is just the first step, and as you have requirements to come forward, just bring more. Okay, next thing I'm going to say is there are two major metric systems that we were asked to support. I'll try to go through them quickly about the characteristics of them, and we'll show a little bit of how we've integrated the two, and if there's questions about them, I can try to answer them. I am not the expert in the two domains, but I can tell you what the thinking was behind the approach. So the two systems that we have support for are StatsD and Prometheus. StatsD is a very simple push protocol. Essentially, any process that wants to emit metrics, you tell it where to send the metrics, and as an event occurs, it will write a little bitty teeny tiny string off to that endpoint. So in most cases, it's a UDP fire and forget packet, which means it can be lost. The benefit of StatsD is that the monitoring system is centralized, so you can say send all these metrics to one place, you know the location, and the network will carry them all there. The granularity of the events is relatively small, so if you want to get really high accuracy on things like distributions of time spans, every transaction that's completed, you can write another UDP message, StatsD metric that says this is how long it took, and then on the back end, you can process those nice distributions. But it's a push system, so what happens in a push system usually is that if you have a lot of things that are pushing metrics, sometimes you can overwhelm the system that you're targeting. So that's one of the downsides. Prometheus is a pull-based system. It's a pretty modern system. It's kind of grown up along with Kubernetes. And as a pull-based system, what ends up happening is each one of the systems that you have that wants to emit a metric, it essentially exposes an endpoint that the Prometheus server can then scrape to get the data, the information about all the meters that are presented to the monitoring system. So the problem there, or the concern you have there with the pull system, is that you now have a centralized set of agents that are going to get the data. They have to know how to find the systems to go off and get. So a core piece of the Prometheus solutions are the ability to have extensible service discovery mechanisms. So in Kubernetes space, you can actually configure it so that it goes off to Kube API server and says, give me a list of all the services with this annotation, and we'll scrape all those things. So for us, we start a peer, we define a service, it says, this is the endpoint for scraping metrics, it's annotated that way. Prometheus goes off the API server, says, give me all the service instances that meet this criteria, and it goes off and scrapes them on a particular interval. It then takes all that data that gets back and aggregates them into a time series database, and then can surface additional metrics that can be used to graph that information on Grafana, or they can be kind of monitored inside of Prometheus as well. Usually Prometheus is not used to do the graphing. Almost always the solution that's going to happen after is going to be based on Grafana. So those are the two basic things. You've got StatsD, which is a push system. You've got Prometheus, which is a pull system. Because they're so different, and because we're IBM, we can't do one, we have to do both. So, how do we do both? Well, my feeling has been since day one that Prometheus is definitely the more modern of the two systems, and it's more flexible, and it's definitely getting a lot more attention. So we wanted to make sure that whatever we did had first-class support for Prometheus. So we took a look at what their client does for emitting metrics, and essentially they break things down into 4 things. And if you guys can see my screen, we'll kind of go through those things right now. Whoops, we'll go through those. So the first thing is each of the metrics has a name, and they characterize the name into 3 sections, which actually isn't here. There's a namespace, a name, and a hang on one second, it's missing one of the fields here. A namespace, a subsystem, and a name. And with the 3 qualifiers, you can basically establish the scope of what the metric is. So that's the name of the thing. So if you look at something like what we have in the chain code, we have chain code launch duration as the name of the metric. So you get an idea of how long it's going to take to actually launch some chain code using our backend. The next big thing that we have are the notion of labels. And labels are essentially dimensions across the time series database that Prometheus keeps track of. So within a metric, you can differentiate an invocation of chain code 1 from chain code 2 by using the chain code label. So now you can filter on that, and you can get additional statistics and do derivations based on that name. Success tells you whether or not the invocation you got back was successful. Was it a 200 or was it a 400? That's basically the gist of like a chain code metric. So now we have the structure that tells us the name of the metric, has metadata about the labels, each label has a value, and that's what gets scraped by Prometheus and ingested into the time series database. For StatsD, StatsD only lets you send essentially stringified buckets. They're called buckets. They're names of things that are dot qualified collections of things. So we needed a way to map the Prometheus collections of namespaces, subsystems, and names down to a StatsD metric or StatsD bucket. But we also wanted to include information about the labels so we could basically allow people who are using StatsD to get additional information so they wouldn't lose a lot of the benefits of what we're trying to capture. So our first pass was to use a system called GoKitMetrics, which essentially dropped all the labels, so we had to work around that by creating our own little structure here with a StatsD format. And what we do with the StatsD format is we essentially take the namespace, the name, and the subsystem, we use that as the stem, and then we'll extend it given whatever pattern the metric author gives us as that format. So in some cases, there'll be hard-coded strings in there, like a prefix on the actual value. Sometimes it's just going to be the value itself. But at the end of the day, you get back this string that tells you this is what the actual StatsD metric is. So I'm going to pause there. Any questions so far?
Are you going to push data and you're going to pull data and then you're going to put it in one database?
No. You have two options. You can use a push-based system, which is only supporting StatsD. And what that means is you configure all of the entities, the orderers and the peers, to send their metrics to some location. So you get basically a protocol, whether it's TCP or UDP, and an address and a port to send it to. So that's StatsD. Your other alternative, other than turning it off, is to have the pull-based system enabled, which is Prometheus. Prometheus, what you do is you specify the name of the URL handler, so /metrics is the path that we typically use, and you give it a port to listen, to expose itself on. And when you run Prometheus, you point Prometheus at all of your server instances, and it will go off and scrape them on sim interval.
So whether I choose which of the options, I can get the same data.
Similar data.
So what's the point of trying to convert it from Prometheus to StatsD format?
So we have friends who wish to not pull the information from Prometheus. Even though Prometheus is a more modern system, we don't want to expose a listen address to the network. They don't want to set up the infrastructure to go off and do service discovery and find that. So instead, it's easier for me here in team, for example, to just say, send all the stats to 1.2.3.4, and then with one small configuration, everything shows up at that target. As opposed to Prometheus, which is, I have to go through some additional effort to make sure that Prometheus can discover everything it has to monitor and pull it all down and aggregate it. So Prometheus metrics are richer because they have dimensions. StatsD is just a bucket. Prometheus is richer in terms of what it allows for queries. Like you have to do a bunch of magic to make things work. So it's just different systems, different philosophies. And the idea was we had to support both. Again, this is because we're IBM. If we were most other places, we'd start with one, see what the market said, see if it broke, see if it worked, right, and adjust based on feedback. But we'll do both because we can.
So you're saying that for StatsD, you have two chain codes and either success or a failure. StatsD would generate 4 buckets.
Correct. You would see chain code, launch duration, chain code 1, dot success. You'd see chain code, launch duration, chain code 2, success. You'd see chain code, launch duration, chain code 2, fail, chain code 2, success. So you'd see 4 separate buckets. Now, the same sort of thing happens with Prometheus as well, in that Prometheus keeps track of all the dimensionality in the same way. So you'll see the combinations as you actually pull the endpoint. It's just that it's more structured coming back. It separates out the label values from the bucket name. The core piece of the metric allows you to do more analysis than you get with simple StatsD. With simple StatsD, you can basically aggregate across them, and you can graph them in different lines. You can do all kinds of things with them, but it's harder to know in advance what you're going to get. For example, there's no way to go to a StatsD endpoint and say, tell me what metrics you provide. Whereas with Prometheus, when you hit the endpoint, it tells you the name, it tells you the type, and it tells you the values, and it tells you the labels. So you have the ability to actually hit the endpoint and understand what's coming back to you.
And one last Prometheus-related question for our application, I guess. Does Prometheus come with a service discovery mechanism that they, treat as a first-class citizen? How does service discovery work?
They have about 10 plugins that you can use. So Kubernetes is one of them. Static is one of them. So I'm using Static for the demo, for the playback. Console is one. There's a programmatic one that you can just basically generate a JSON document. It'll constantly refresh the JSON document. There's all kinds of methods that they support. But again, since they've grown up with Kubernetes, the one that's most popular right now is to basically use the annotated services. So you can basically say this is a scrape service. Prometheus goes to the API server, finds out where all the endpoints are, and then scrapes them. Okay. So that's the basic idea of the two systems. There are 3 different kinds of metrics that can come out, and they are gauges, counters, and histograms. So gauges are used to reflect a value at a certain point of time. They are probably the least flexible and least common of the different kinds of metrics that you're going to see, but they're useful for things where you're basically echoing some other data source. An example of the gauge that we produce in Fabric is information about the number of Go routines that are currently active, or the amount of memory that's currently active in the system. So we'll go off and we'll ask the Go runtime, can you tell us how many Go routines you have active? They'll tell us, and we'll reflect that out as a gauge. So that's a point-in-time value. Histograms essentially are a collection of buckets, and within the bucket, you have a certain range. So essentially, you'll say things like, if it's less than or equal to some value, I'll increment the counter in this bucket. So you'll see progressions of something like, 1 millisecond, 10 milliseconds, 100 milliseconds, 500 milliseconds, 1 second. And if you have a request that takes 250 milliseconds, it'll add counts to the bucket that includes 250 and everything that's greater than that inside the histogram. And you can then use tools to analyze that to find out essentially what your decay is, where your 99th percentile is, what your 95th percentile is, all estimations from that histogram. So we use histograms largely for time series data. So if we want to find out how long something took, we will almost always record that in histograms so we get a feeling for the distribution. And the one that's most common is the counter. So a counter is really just a monotonically increasing value. So you'll see things like number of transactions processed, number of invocations as counters. And if you go back to what I said about histograms, even histograms are just a collection of counters per bucket. So how many times did I have a value that was less than or equal to this? I'll just increment that counter. So those are the 3 basic metric types that we have. And everything is based on these 3.
And then the histogram bucket, so you can define the bucket size and everything, or?
We can, you can't.
Okay.
Okay? So I say that way because the way Prometheus works today, they actually have 2 different kinds of data structures that allow you to keep track of distributions. One is called, I think it's called statistics or something. I forget what the actual number is, what the actual name of it is. But essentially what that one does is it keeps track of all the data points within the process memory space. And then it uses a sliding window to determine the right size of the buckets. But even there, you have to tell it information. For example, if you're looking for a 99th percentile response time of less than 300 milliseconds, you'll define buckets that include your SLOs so that you know when you've met your SLOs and you've exceeded your SLOs. So you have to know up front what you're going to do there. Histograms, you don't have to know as much about it, because you have to pick something that's sane for the domain that you're in. So the defaults that we have in the code and the defaults that we've inherited from Prometheus are good for simple request response stuff. So it's a geometric progression that goes from about 250 milliseconds or 250 microseconds up to about 2 seconds or 3 seconds. There's a progression of buckets, and that captures most of your typical things. If we need to tune it, we do have the ability to tune the buckets in our own options here. So here in the histogram options, we have the ability, we have right here. We have the ability to put in the buckets ourselves. So if we find that we have a meter that's blowing out things or it doesn't make sense, we can just go back and tune it. Okay? But it's not going to be exposed. And this is going to come back to another one of mine. If you haven't met me before, I have lots of philosophies. One of them is that if you provide too much configuration, in addition to complexity for you, it's overload for everybody else. It's much better to avoid all of this stuff and just have sane behavior that you can rationalize, right, than to try and give them so much information up front that they get to analyze it and they get paralyzed by trying to figure out the right information, right? So if we need to add it, we can. It's trivial to do. It's literally changing one line of code. We do it, we move on, we go. All right, so with that, I've pretty much shown you this is what the code looks like. You define your counters using these little options, so it's not hard to define them. And then when you want to go off and track one of them, let's go to something like the handler. You reference your counter. For example, in this case, it's shim request received. You provide the values for the labels, and you just increment the counter. So the hard part is really defining the options and the names, and then just a little bit of code instrument to raise the metric. So it's light touch, right? It's spread all over the code base, which is not ideal, but it's light touch. All right, so I've gone through the first three things on my list, which is to give you a definition of the interfaces, tell you about push versus pull, and to show you what the code looks like inside. So now I will take a moment and I will go over to this. So while I have been talking, I have been running in the background a collection of tasks that are just invoking queries and calling chain code on a small network that consists of 4 peers, 2 orgs, each with 2 peers of the Kafka-based order. And the whole point of this was to just get some information out there that we can take a look at. So this has been running in the background, heating up my laptop. Now, one of the common questions that we tend to get is, what are the collections of metrics that we currently export? So what I'm going to do is I'm going to grab this. This is essentially how Prometheus is going to scrape an endpoint, right? In order for Prometheus to scrape information about the metrics, when we configured the peer, we gave it a CA, we gave it a cert, and we said that we require client certificate authentication from Prometheus to basically pull the information to us. So this is a big curl command that does the same basic thing. I'm pointing to the keys, I'm pointing to the certs, I'm pointing to the CA to be able to hit that endpoint. And here you'll be able to get a feel for what is actually maintained for the peer. If I can copy and paste. Okay. So when Prometheus goes off to a peer and says, give me all the data, this is what the peer sends back. And if you take a look, you'll see that the first thing that comes back in the format of the data is information about what the thing is that you're looking at. So you can see there's a help field that says chain code launch duration is the time to launch a chain code. So it kind of self-describes what this stuff is. The type tells you the type of the data that you're looking at. So this is a histogram. So since it's a histogram, we're going to find essentially 3 different kinds of information associated with this particular meter. We're going to find buckets. In this case, we have 10 buckets. And they represent the number of times a particular value has been hit that's less than or equal to whatever this number is. So in this case, if its launch duration is in seconds, it's 5 milliseconds, 10 milliseconds, 25, 50, 100, 250, half, 1, 2.5, 5, 10, or more than 10, right? So that gives you an idea of the distribution of the time. The sum tells you the total amount of time that you spent, and the count is the number of times you hit it. All right, so for us, this launch duration was less than or equal to 5 milliseconds, and you can see here is actually 0.6, because that's the sum. So we have information about the launch duration. To Costas' earlier question about the labels, we can see here that each of the different chain codes has a different label value. So the same set of information is actually duplicated across each one of these dimensions. So CSCC for configuration has one collection, right? LSCC's got a separate one, and then the chain code I'm using for test has got yet another down here. The next one that we're going to hit here is going to be the shim request duration. And here we have labels that basically represent the operation. So when the chain code's running and it calls back to the peer and it says, get me the state, give me the state by range, put the state, we get an idea of how many times each of these operations was called, how long it took, and what the chain code was that was running when that happened. And so this gives you some information about what's going on. Then we have chain code shim request completed, chain code shim request received, information about the deliver blocks, information about how long it took to build things, Go information about garbage collection time, the version of Go that we're using, memory statistics. There's a whole bunch of stuff that's in here. And if you go beyond all of that, we'll get to the things that are kind of going to be a little more fun. So as part of wiring in the metrics, almost all of what we do in the peer and almost all what we do through the orderer enters the system using gRPC servers. So in order to capture a fair bit of information at, I guess, pretty close to free, you just instrument one little bit of code. We added metrics to our server-side interceptors for gRPC. So every request that's made to a gRPC endpoint within the peer or the orderer, you actually collect metrics on. Now, they don't have the domain context. For example, like the endorser, if it comes back with an endorser code of 200 versus a 400, that won't be captured here. But you will know that you're calling something like process proposal, and you will know how many times you called it, and you will know how long it took for those calls. So you can see here that we have these server streams and unary stream buckets that are all kind of captured, and the completion codes are there as well. So you get a feel for what the distribution looks like. Were they successful? Did they fail? Did the client close it? That sort of thing. Ledger block processing time and transaction counts. So that's essentially what we have right now for the peer. For the orderer, we have a little bit different set of metrics. Here we have information about things like the broadcasting queue duration, how long it takes to queue a transaction, the number of operations that we've processed, information from Kafka about the compression ratio, bytes per second on the topics, request latency. Since we have embedded the etcd client, etcd is showing us its metrics. These are only available in Prometheus because it doesn't do anything with statsd, but it's interesting that it's there. Since etcd is already metered for Prometheus, it's already instrumented for Prometheus, it shows up for Prometheus. But since it's not using our abstraction, it does not show up as statsd. So this is an example of where we have something in Prometheus for free, like true for free, that we will have to at some point rework for statsd.
If we were to start doing work on having metrics for us right now, is the backend ready, or do we need to do some?
So the backend's ready. Like all the stuff is here. You guys can do this. I'm saying that etcd today, the etcd client that you have, is already wired to emit Prometheus metrics. So we are seeing the etcd metrics from Prometheus today. If statsd is used instead, they're not instrumented with statsd. So you will have to go off to basically mirror this information from Prometheus to statsd. But it gives you lots of information. The write-ahead log is probably the one that's going to be most important for us to see when we actually turn that stuff on. All right, so those are the kinds of metrics that we've got. So now I guess the end of it would be start Prometheus. So this is Prometheus. So for fun, I was just playing around this morning, trying to come up with a couple of different graphs to give you an idea of the sorts of things you can get today. I don't expect you to be going ooh, ah, or anything crazy like that. But it's a pretty straightforward example. So this first graph that I'm showing here, you can't really see it, but the query says the max of ledger blockchain height minus the min of ledger blockchain height. And you can see this value is basically going up and down from about 4 to about 25. And what this is showing us is that across the 4 peers that we have in our network, at one point, a peer can be as many as 25 blocks ahead of the other one in terms of commit. So this gives us an idea of what the skew looks like. It's a very simple query to get that information. It's kind of nice to see where we are. The nice thing here is it's not growing. We're not falling behind, right? It's staying within some bounded range. But it's just a data point. The next one I'm looking at is histogram quantile 0.5, rate of the unary survey request duration of process proposal. So to translate that into English, we're looking at the number of times that process proposal has been called within a 5-minute window. We're finding that rate, and we're going to graph it. And when you run the query, you get a handful of pieces of data back, and if you graph it, and you reload, we can see that the average response time that we're seeing on process proposal for 2 of the peers is about a half a second, and for the other 2, it's down around a tenth of a second. Now, I can explain this because one of the chain codes I'm calling is sleeping for a random duration between 0 milliseconds and 1,000 milliseconds. So on average, I should see around a half a second as being the duration of this call. So with our 4 peers, we have 4 data points on here. It gives that information. That's just coming from the metrics that we have today. Next graph that we have is gRPC COM. So that's the COM layer gRPC. Connections opened minus connections closed. One of the things that we've found in the past in some of the client issues is that we have people who connect to gRPC service and never clean up their connections. So what we'd expect to see is if that was happening, these connection deltas would grow. But since I have a relatively well-behaved trivial application, we're just finding that the connections are staying within a particularly small region. We can see that they're opening and closing them at some particular interval. But you can see this information now. So you can now take this information, and in addition to reporting it, you can now alert on it. So if you find that you have been growing the number of connections over the last, 40 minutes, right, then you have an idea that something might possibly be wrong. Okay, this one is rate of ledger blockchain height over a 1-minute interval. So what this is essentially saying is I'm going to look at the rate of change over the last minute of the height of the blockchain. So this is basically how many blocks per second I'm adding over a minute. And that's your basic graph. And we can see that over the last hour or so, as I do other things, the value is kind of slowing a little bit. It's coming down. It might be indicative of some other problem. Maybe it's a leak, maybe it's a storage issue, we don't know. But we can actually kind of see that right now that's happening. Don't be scared of this. This is when I close my laptop load. So you can see that too. Okay. Next one, ledger transaction count. So we want to get an idea of how many endorser transactions we ran. On-chain code, MyCC version 0. So over a 5-minute interval, I want to get an idea of the rate at which I'm invoking this. So this is what's happening for my invocation of endorser transactions over a 5-minute interval, and this is the basic rate that we're running at. So we started out at about 5, and now we're down to about 3.5. I'm just going to say it's because of WebEx. I don't know. I'm just going to pretend. So those are the kinds of things that you can get now. It's easy with Prometheus because you can just define your queries right here, then export them to Grafana. StackD is a little bit more work to do FlexD and a few other things, but that's the basic idea. So with that, that's pretty much all I had to show was that we now emit them, you can graph them, they are usable. The next big step is we're going to take these definitions that we have of the counters and the gauges and the histograms, these literals, and we're going to write a tool that extracts that out into a markdown document so that the ID folks can just stick that inside of the info center, and that will encapsulate all of the metrics that we provide for Fabric in one place. That's all I got.
Who's an SRE here? Standing ovation, right?
Sweet.
So a few things when we put this in action in IBP2, currently IBM metric service does not have any way of showing Prometheus metrics. They don't have any solution for it.
No, they still use Lumberjack.
Is that?
You're still using Lumberjack.
Yes,
Yeah.
you're still using Lumberjack. So we'll have to, if we go Prometheus way, we will have to use the Prometheus to Graphite converter and send metrics to the IBM metric service, or we'll just use StatsD option and send it to the metric service. So you will still, SRE will still be using IBM metric service and the graphs that you've been using for now until IBM has a Prometheus option. Oh, okay. So what Andrew said is logging service is changing and metric service in IBM is also changing to some other new solution?
Yeah, right. So metric service is changing as well. Hopefully they'll support Prometheus, but yeah, that was the biggest reason that that StatsD was on the table for us, was that the metric service we used didn't support anything else really. But hopefully that will change soon, or at some point next year.
It's there. My perspective is that it's there. It's probably not the path that we want to push people down. So I'm saying that more so that when we start talking about samples, documentation, things for the project itself, not the commercial things around it, you're probably not going to see a whole lot of StatsD. You're probably going to see more things that basically say stay away from it unless you really need it. And I don't want you to be afraid of that. It's just a matter of it's not as easy to use or quite as capable.
Yeah, no, I completely agree, right? That StatsD was really for people who are already using it, but if you're starting out from scratch, go Prometheus for sure.
Other unrelated things that you might want to be aware of in terms of ops and serviceability, we've done a bit of changes to logging. In particular, we've added some interceptors to log some of the requests that are coming through. We've more fully embraced context-based logging in a few places. We have a whole lot more to do there, but you'll start seeing things like this, where we have key value pairs associated with a particular line of output. These aren't thump strings anymore, right? We're going to start getting to the point where we actually can carry along with us information about, the origin of the request and some metadata. And the messages will start to be focused more on what we want to log, not from a human perspective necessarily, like, here's a human-readable English text message, but one that allows us to more quickly discover patterns when we're doing postmortems and such. Context-based, if you start looking at context-based logging, you'll get a good idea for how people are searching for things. But if you're looking, for example, for everything that's coming from 127.0.0.1, 5.88.3.1, right? If you're looking for that client, it's easier to find tier address equals that and get all of your log records that have that information than something else. You'll also see us start talking about spans. So probably it's not going to happen in 1.4. It probably isn't going to happen in 2.0. But we are going to start adding some of the interceptors for gRPC tracing, which means we establish spans. And establishing spans allow us to basically follow a transaction path from a client through all the peers that it communicates with and the order and everything else. So that's going to allow us to really see an end-to-end picture. So that's the next logical step. Now the interceptors are in place. It's just adding, right? We have the frameworks in place. We'll just keep adding little bits as we go along. Other things. If you want to get information about the run and go routines, you do not have to kill the process in the orderer anymore. You can just send, say, user 1, just a signal, and we will log the status of all the go routines. So what that means is we're starting out with something simple, right? Getting go routines, but more importantly, we now have the hooks in place to allow us to add more diagnostic information. So if we need to find out later on that it's not just the go routines that we want information about, we want to find out information about the last 50 errors that occurred, or some other thing that we can have in the process space, we can start to carry that information and actually surface that out for people to use. We've introduced health checks. The only one that is implemented today and actually works is Docker. So what that means is, for example, the readiness check for Kubernetes. If you're starting up a peer and the peer comes up, but the Docker server inside of it actually isn't running right now, the peer will say it's not healthy until it can actually connect to Docker and everything is cool. And in the process, right, while you're doing that health check, it'll tell you Docker is down, Docker is down, Docker is down, Docker is down. Once it comes back up, the status code of the responses goes from 503, service unavailable, to 200, everything's okay. And you can use that to keep things, you can use that both as a liveness check and a readiness check. Yeah, so that's I think the highlights of a lot of what we do.
Pretty good.